Hello learners, I am Dr. Munish Kumar Bharadwaj from School of Engineering and Technology of IGNOU. As you remember, we were discussing about the defects in steel, and in this series, in this lecture, I'll discuss with you the corrosion of steel and effects of concrete environment on corrosion. Let us begin with corrosion of steel. Concrete normally provides reinforcing steel with an excellent protection against corrosion due to the environmental forces. Where there is a moisture, corrosion of steel is possible. Corrosion eats into concrete, steel, and the very foundation of man's attempt to build. It can destroy not just the homes but bridges, industrial plants, and any other construction where structural steel or reinforced concrete with steel are used. The effects are slow, but the results are catastrophic. Thus, there exists a compelling need for you to know adequately about the corrosion to safeguard your buildings and other infrastructure. The high alkaline environment in concrete results in the formation of a film which passivates the steel and protects it from deterioration caused by corrosion. In addition, concrete can be proportioned to have a low permeability which minimizes the penetration or ingress of harmful constituents. Low permeability also increases the electrical resistivity of concrete, which impedes the flow of electrochemical corrosion currents. Because of these inherent protective attributes, corrosion of steel does not occur in good quality concrete elements or structures. Because of these reasons, the corrosion will not take place. Corrosion of steel, however, can occur if the concrete is not of adequate quality, the structure was not properly designed for the service environment, means the structure should be designed keeping in view its service environment, or the environment is saline like in coastal areas, because in coastal areas the environment is saline, or with alternate splashing sea water or brackish groundwater and gaseous emissions in industrial regions. So these are some of the reasons which may cause corrosive environment. Now let us understand principles of corrosion. Corrosion is an electrochemical process. The corrosion process is similar to the action which takes place in a flashlight battery. What happens there? An anode where electrochemical oxidation takes place. There is a cathode where electrochemical reduction occurs, and an electrical conductor and an aqueous medium is there. Any metal surface on which corrosion is taking place is a composite of anodes and cathodes electrically connected through the body of metal itself. Reactions at the anodes and cathodes are broadly referred to as half-cell reactions. At the anode, which is the negative pole, iron is oxidized to ferrocene, that is, Fe is converted to Fe++, it is converted to iron, and with the release of 2 electrons, the iron, that is Fe++, is subsequently changed to oxides and hydroxides of iron by a number of complex reactions. the volume of the reaction products is several times the volume of iron. Means the rusted iron have much more volume in comparison to the healthy iron, and it is almost 7 times. The volume of the corroded iron is 7 times the iron which is not corroded. What happens then? It gives rise to increasing tensile stresses in concrete, because when the volume is increasing, then it will put pressure on the concrete. So what will happen there, that tensile stresses will occur in the concrete, which will result in cracking, spalling of concrete cover and rust straining, etc. So these will be the results, outcome of that. Corrosion is a continuous, irreversible process caused by various factors. Now, let us understand how oxygen is available in concrete. The availability of oxygen is one of the main contributory factors for corrosion of steel. A number of investigations indicate that if the steel passivity is destroyed, conditions will be conducive to the corrosion of steel reinforcement in those parts of a concrete structure that are exposed to periods of intermittent wetting and drying. You saw that by its nature, concrete is providing a protection to reinforcement from corrosion. In wet concrete, dissolved oxygen will primarily be diffusing in solution, while in a partly dry concrete, the diffusion of gaseous oxygen is much faster. Now let us understand the importance of chloride ions in corrosion process. The intrusion of chloride ions in reinforced concrete can cause steel corrosion if oxygen and moisture are also available to sustain the reaction. Means these two things also be there for sustaining that reaction. What is that? Oxygen and the moisture. Chloride ions may be introduced into concrete in a variety of ways. What are these ways? Some are intentional inclusion. How? It as an accelerating admixture. Means when we are adding accelerating admixture, then the compounds may be having chloride. Or accidental inclusion as contaminants on aggregates, or penetration by de-icing salts, industrial bryons, marine spray fog or mist, etc. Now let us understand electrochemical role of free chloride ions. There are 3 theories to explain the effects of chloride ion on steel corrosion. First one is the oxide film theory. What does it say? It is believed that an oxide film on a metal surface is responsible for passivity and thus protection against corrosion. This theory postulates that chloride ions penetrate the oxide film on steel through pores or defects in the film easier than the other ions like sulfate ion. Alternatively, the chloride ions may colloidally disperse the oxide film, thereby making it vulnerable to penetration of corrodants. Second theory is the adsorption theory. Chloride ions are adsorbed on the metal surface in competition with dissolved oxygen or hydroxyl ions. The chloride ion promotes the hydration of metal ions and thus facilitates the dissolution of the metal ions. Then corrosion takes place. The third one is the Transitory complex theory. According to this theory, chloride ions compete with hydroxyl ions for the ferrous ions produced by corrosion. A soluble complex of iron chloride forms. This complex can diffuse away from the anode, destroying the protective layer of iron hydroxide, permitting corrosion to continue. Since corrosion is not stopped, more iron ions continue to migrate into the concrete away from the corrosion site and to react with the oxygen to form higher oxides, which results in a fourfold volume increase. It is the expansion of iron oxide that produces internal stress, which eventually cracks the concrete. Because with the increase in volume, there are stresses on the concrete, and these internal stresses may cause the cracks in the concrete. Now, let us understand the corrosion rate and pH value. The corrosion rate of iron is reduced as the pH increases, because this process of corrosion is favored under low pH. Since concrete has a pH higher than 12.5, it is usually an excellent medium for protecting steel from corrosion. Only under conditions where salts are present or the concrete cover has carbonated does the steel become vulnerable to corrosion. Only under the conditions where salts are present or the concrete cover has carbonated does the steel become vulnerable to corrosion. In the process of carbonation, the atmospheric carbon dioxide reacts with the alkaline material in the concrete and convert them into carbonates. Thus, alkalinity of concrete is reduced in terms of pH value. When pH value falls below 9, the process of corrosion commences. Now let us understand passivity and transpassivity. Passivity of a metal is generally characterized by a thin and tightly adherent oxide film on the metal surface, which tends to protect the metal against further corrosion. The exact composition of the thin and normally invisible film has been difficult to determine. However, investigations reveal that it is made up of chemical combinations of oxygen and hence called oxygen film. When a potential is applied to an iron electrode, the rate of current flow depends on the state of passivity. Concrete is generally passive such that little current flows when a potential is applied. However, if the potential is progressively increased, eventually the current will flow. This is because at this point oxygen is evolved and the electrode reaction involves the electrolysis of water. What happens in electrolysis of water? The water is then electrolyted to hydrogen ion and release of electrons. As you see in this reaction, twice H2O, that is equal to 4H plus O2 plus 4 electrons. This phenomena is called transpassivity. Neither steel nor concrete is durable in a low pH. Low pH means acidic environment. Now let us understand what is stress corrosion cracking. Stress corrosion is defined as the process in which the damage caused by stress and corrosion acting together greatly exceeds that produced when they act separately. Now in case of stress corrosion, the stress and corrosion both are acting together and they produce the effect much more when they are acting separately. In stressed steel, a small imperfection caused by corrosion can lead to a serious loss in tensile strength as the corrosion continues at the initial anode area. Now let us see the effect of temperature on steel. It is found that there will not be any appreciable reduction in strength in steel reinforcement up to a temperature of 300 degrees centigrade. However, the experiments indicate that at this temperature, the bond between steel and concrete gets disturbed and concrete starts spalling, exposing the reinforcement to outside environment, which may ultimately lead to corrosion of reinforcement. So this can happen at 300 degrees centigrade. The mechanical properties of cold twisted deformed bars such as Tor steel are unaffected up to 300 degrees centigrade. Beyond this, there will be continuous reduction in proof and tensile strength of the material. At about 600 degrees centigrade, the reduction will be almost 50%, rendering the same structurally unsound. Means if the 50% strength is lost, then certainly it will become structurally unsound. Here you see the two graphs showing the reduction in proof strength of steel at elevated temperature. In first one, you see the graph on x-axis, the temperature is there. On y-axis, ratio of proof strength is given. In second figure, you see the ratio of proof strength on your left, and on your right you see the fire damage factor, and on x-axis temperature in degree centigrade is there. So you see that with the increase in temperature, the strength is lowering down, decreasing. In both the cases, you see this effect. Now let us understand the effect of concrete environment on corrosion. How the concrete environment affect the corrosion process. First of all, we will look into the material or the ingredient of the concrete, the main ingredient, the cement. Let us begin with the Portland cement. When Portland cement hydrates, the silicates react with water to produce calcium silicate hydrate and calcium hydroxide. The following simplified equations give the main reaction of Portland cement with water. Here you see the reaction of trisilicate with water, and also in second reaction, the reaction of disilicate with water. Finally, in first equation, it is forming twice CaO2 SiO2 thrice H2O plus thrice calcium hydroxide. In second reaction, it is forming thrice CaO twice SiO2 thrice H2O plus calcium hydroxide. You know that the high alkalinity of the chemical environment normally present in concrete protects the embedded steel because of the formation of a protective oxide film on the steel. The integrity and protective quality of this film depends on the alkalinity, that is the pH of the environment. Higher the pH means more protective layer. Lower the pH means less protective. A well hydrated Portland cement may contain from 15 to 30% calcium hydroxide by weight of the original cement. This is usually sufficient to maintain solution at a pH about 13 in concrete, independent of the moisture content. So you now understand that how this concrete environment is alkaline. This is because of the presence of calcium hydroxide. And as you see here, that how much amount of calcium hydroxide by weight is there, it is 15 to 30%. And because of the presence of calcium hydroxide, because it is of basic nature or alkaline nature, so the concrete is having alkaline nature. And due to this alkalinity, corrosion of steel should not be there. But there are reasons, there are factors which causes the corrosion. Even for cements with such high reserve basicity, the alkalinity may be reduced in a number of ways. What are these ways? Reduction of alkalinity by leaching of soluble alkaline salts with water is an obvious process. Means these alkaline salts are leaching out with the water from the concrete. The partial neutralization by reaction with carbon dioxide, that is carbonation, as present either in air or dissolved in water, is another common process. What does it mean? That the carbon dioxide that is present in air or dissolved in water, that reacts with carbon hydroxide and it forms calcium carbonate. Means it is converting the calcium hydroxide into calcium carbonate, means it is damaging the source of alkalinity, and this process is called carbonation, and it makes the concrete from alkaline to acidic. Calcium chloride acts as an accelerator in the hydration of tricalcium silicate as well as to promote the corrosion of steel. Also, the other compounds present in Portland cement like tricalcium aluminate C3A and an aluminoferrite, that is C4AF, augment the process of corrosion. These two compounds, that is tricalcium aluminate and aluminoferrite, tetraaluminoferrite, these augment the process of corrosion. The C3A, that is tricalcium aluminate, reacts rapidly in the cement system to cause flash set unless it is retarded. Calcium sulfate is used as the retarder. Calcium sulfate forms a coating of attrinite, that is C3A thrice CaSO4 32H2O, around the aluminate grains, thereby retarding their reactivity. Let us understand about the aggregate. The most serious problem arises when the aggregates contain chloride salts. This can happen when sand is dredged from the sea or taken from seaside chloride locations. Care should be exercised when using admixtures containing chloride in combination with lightweight aggregates. Lightweight aggregate containing sulfides can also be damaging to high strength steel under stress. So this way aggregates can play their role in causing the environment which is corrosive to the steel. Now water. How water can play a role in corrosion? An important effect of the moisture content of concrete is its effect on the electrical resistivity of the concrete. Progressive drying of initially water saturated concrete results in the electrical resistivity increasing from about 7 into 10 power 3 ohm per centimeter to about 6000 into 10 power 3 ohm per centimeter. Field observations indicate that when the resistivity exceeds a level of 50 to 70 into 10 power 3 ohm per centimeter, steel corrosion would be negligible. Now, how concrete quality affect the corrosion? Concrete will offer more protection against corrosion of embedded steel if it is of high quality. Means high quality concrete will give better protection against corrosion. A low water cement ratio will show the diffusion of chlorides, carbon dioxide and oxygen, and also the increase in strength of concrete may extend the time before corrosion induced stress causes cracking of the concrete. The pore volume and permeability can be reduced by lowering the water cement ratio. Means lesser the water cement ratio, then lesser will be the permeability of concrete and lesser will be the pore spaces or voids in the concrete, and that way we can safeguard the steel from corrosion. Now, thickness of concrete cover over the steel. How it plays its role. The depth of concrete cover over the steel should be as large as possible, consistent with good structural design, the severity of service environment and the cost. Means the good cover will protect the reinforcement from corrosion better. Lesser the cover, then there are more chances of corrosion of the reinforcement. Then carbonation. We discuss something about this carbonation. Carbonation occurs when the concrete reacts with carbon dioxide from the air or water and reduces the pH to about 8.5. At this low pH, the steel is no longer passive and corrosion may occur. For high quality concrete, in situations where the rate of carbonation is extremely slow, carbonation is normally not a problem in very dry concrete or in water saturated concrete. Maximum carbonation rates are observed at about 50% water saturation. And as I told you, that carbonation reaction is that carbon dioxide present in environment or dissolved in water, it reacts with calcium hydroxide and forms calcium carbonate and water. So what we discussed in this lecture, that what is the process of corrosion of steel, how different ingredients affect this corrosion process, how the quality of concrete can play its role in providing better protection to the reinforcement from corrosion. Then we discuss the effect of concrete environment on corrosion. In our next lecture, I'll discuss with you the procedures for identifying corrosive environments and active corrosion in concrete, then steel manufacturing process, then simple field test for structural steel, and also chrome steel, that is chromium in steel. This will discuss in next lecture. I hope you must have enjoyed this lecture. So thank you for watching.